Welcome to the world of the supersonic stovepipe. A ramjet is a fascinating type of jet engine, remarkably simple in its design. Imagine a specially shaped pipe, open at both ends, engineered to perform best when air rushes into it at incredible speeds. We're talking about speeds faster than the speed of sound, known as supersonic speeds. It's an elegant piece of engineering, its brilliance lying in its minimalism. This inherent simplicity is the key to its unique and powerful capabilities. It's often called a flying stovepipe, and for a very good reason. Its fundamental design allows it to achieve feats that other, more complex engines might struggle with. The core concept behind the Ramjet is wonderfully straightforward. Unlike conventional jet engines, which are filled with many spinning parts, the Ramjet has almost none. There are no whirring turbines and no intricate arrays of compressor blades. Instead, it relies on clever aerodynamics and the physics of airflow. This distinct lack of moving parts presents a significant advantage. It means there are fewer components that can malfunction or break, particularly under the extreme stresses encountered during high-speed flight. The engine's own forward motion does the crucial initial work of compressing the air. It's a brilliant idea, harnessing fundamental physics. So, how does this ingenious stovepipe actually generate thrust and fly? It begins by capturing air that is already moving at a very high speed. As this air enters the engine, it is carefully slowed down and, as a result, compressed. Fuel is then continuously injected into this stream of compressed air. This fuel-air mixture is then ignited. The resulting hot expanding gas then blasts out of the back of the engine at an even higher velocity. This powerful expulsion of gas creates a strong forward thrust, propelling the vehicle. This is a continuous, self-sustaining process, as long as the engine maintains its high forward speed. The true beauty of the Ramjet lies in this elegant simplicity. It serves as a clear testament to how fundamental principles of physics can be harnessed to create powerful machines. We can observe how air pressure, its temperature, and its velocity interact in a precisely controlled manner within the engine. This carefully managed interaction is what generates immense propulsive power. The Ramjet truly comes into its own at supersonic speeds. At these velocities, the incoming air itself effectively becomes the compressor. It's a concept that seems almost too simple to be so incredibly effective in practice. Yet this design has powered some of the fastest air-breathing vehicles ever created by humankind. Let's delve deeper into the process of how a Ramjet compresses air. It all initiates at the engine's inlet, the very front of the pipe. This inlet is not just a simple opening, its shape is meticulously designed. This geometry is crucial for efficiently capturing the incoming supersonic air. As this high-speed air enters, it encounters a section known as the diffuser. The diffuser is a part of the engine that gradually widens. This carefully engineered widening forces the fast-moving air to slow down considerably. You can picture water flowing from a narrow hose into a much wider channel. Its speed naturally decreases. This slowing down has a remarkable and vital effect on the air. As the air significantly reduces its speed, its kinetic energy, the energy it possesses due to its motion, must be conserved. It doesn't simply vanish into thin air. Instead, this kinetic energy is transformed into other forms of energy: static pressure and heat. Consequently, the air becomes much denser and its temperature rises substantially. This entire process is known as ram compression. The faster the Ramjet is already traveling through the atmosphere, the more pronounced and effective this compression becomes. It is as if the engine is ingeniously using its own forward velocity to forcefully squeeze the incoming air. No mechanical compressor, like those found in turbojet engines, is required. Now we have this stream of very hot, highly compressed air. This air then flows into the next section, the combustion chamber. Inside this chamber, fuel is continuously sprayed into the airflow. This fuel, often a liquid hydrocarbon, mixes thoroughly with the highly pressurized and preheated air. This potent mixture is then ignited. The ignition source initiates a continuous and stable burn, essentially a controlled, ongoing explosion. This burning process releases a tremendous amount of thermal energy. The temperature inside the combustion chamber skyrockets to incredibly high levels. It becomes an intensely energetic environment, all neatly contained within our flying stovepipe. The extremely hot, high-pressure gases produced by the combustion process naturally seek to escape. They are channeled towards the rear of the engine. To exit, they must pass through a specially shaped exhaust nozzle. This nozzle is designed to accelerate these hot gases to even higher speeds as they are expelled. This rapid expulsion is key. According to Newton's third law of motion, for every action, there is an equal and opposite reaction. As these superheated gases are violently ejected backwards from the nozzle, they create a powerful forward thrust. This thrust is what propels the ramjet and the vehicle it is attached to through the air. The entire cycle repeats continuously. One of the ramjet's most compelling advantages is its inherent structural simplicity. As we have explored, it notably lacks major moving parts. There are no complex turbines spinning at high speeds, nor are there intricate arrays of compressor blades. This characteristic makes it mechanically simpler than many other types of jet engines, such as turbojets or turbofans. This simplicity often translates directly into lower manufacturing costs, particularly for single-use applications. Furthermore, it generally means increased reliability. Fewer moving components mean there are fewer things that can wear out, jam, or break down under operational stress. This robustness is especially valuable. This absence of heavy, complex machinery contributes directly to another key benefit. Ramjets typically possess a very high thrust-to-weight ratio. This means they can generate a substantial amount of propulsive thrust for their relatively low physical weight. This characteristic is absolutely crucial for applications where high speed and agility are the primary requirements. Consider vehicles that need to accelerate very rapidly to high velocities or maintain those extreme speeds for extended periods. The Ramjet offers a potent yet comparatively lightweight propulsion solution. It's an engineer's ideal for certain high-performance flight scenarios, enabling greater payload capacity or extended operational range. Ramjets truly come into their element and excel at supersonic speeds. Their operational efficiency tends to increase as their forward speed increases, typically becoming most effective above Mach 2 or Mach 3, that is, 2 to 3 times the speed of sound. At these high velocities, the ram compression effect is exceptionally strong and efficient. This allows the engine to process vast quantities of air effectively, converting its kinetic energy into pressure with great success. Traditional turbojet engines often encounter performance limitations or become significantly less efficient at very high Mach numbers. The Ramjet, in contrast, thrives in this demanding high-speed environment. Given these distinct characteristics, where do we commonly see ramjets in practical application? Their primary and most widespread use is in powering missiles. Many long-range air-to-air missiles and surface-to-air missiles rely on ramjet propulsion. These advanced weapon systems need to reach their targets very quickly and often cover substantial distances. Ramjets provide the necessary sustained high speed and thrust to achieve these mission objectives. They are also employed in some high-speed unmanned aerial vehicles, often referred to as drones, and in specialized target vehicles used for military training exercises. Experimental aircraft, designed to push the boundaries of atmospheric flight, have also utilized ramjet technology. Despite their impressive performance capabilities at high speeds, ramjets possess a fundamental operational limitation. They cannot produce any static thrust. This means a ramjet engine is incapable of starting its operation from a standstill or zero forward velocity. The crucial ram effect, which compresses the incoming air, only begins to work effectively when air is already rushing into the engine inlet at a significant velocity. Typically, a ramjet needs to be moving at supersonic speeds, often around Mach 1, the speed of sound or higher, before it can light up and sustain its operation independently. This requirement presents a practical engineering challenge. So, how do vehicles powered by ramjet engines actually get moving in the first place? They invariably require an auxiliary propulsion system to achieve the necessary initial speed. This initial boost could be provided by a solid-fuel rocket booster, which is a common solution for many missile applications. The rocket accelerates the entire vehicle up to the ramjet's minimum operational speed. Once that critical speed is reached, the rocket booster might be jettisoned, and the ramjet engine then takes over, sustaining flight. Alternatively, a larger mother aircraft could carry the ramjet-powered vehicle to a high altitude and sufficient speed before releasing it. Another significant challenge associated with ramjets is their inherent inefficiency at subsonic speeds. When operating below the speed of sound, the ram compression effect is quite weak. The engine simply cannot compress enough air effectively to support efficient combustion and thrust generation. This makes them generally unsuitable for aircraft that need to operate across a broad spectrum of speeds, including crucial phases like takeoff, loitering, and landing. Their design is highly specialized and optimized for the supersonic flight regime. This specialization naturally narrows their range of potential applications when compared to more versatile engine types like turbojets or turbofans, which can operate from standstill to high speeds. Finally, operating at very high supersonic speeds, where ramjets excel, brings with it the problem of extreme temperatures. The air entering the engine is already significantly heated by the process of ram compression. Then, the combustion of fuel inside the chamber adds an enormous amount of additional heat. These incredibly high internal temperatures can pose a significant challenge for the materials used in the engine's construction, particularly in the combustion chamber and exhaust nozzle. These components must be able to withstand these fiery conditions without melting or failing. Managing these intense thermal loads is a critical aspect of ramjet design.